Okay, so welcome everybody to today's IAMP One World Mathematical Physics seminar. It is my great pleasure to introduce Tomaz Prosen from Ljubljana, and Tomaz will tell us about random matrix spectral fluctuations in quantum lattice systems. And let me say that, as usual, the seminar will be recorded and made available on YouTube. So I leave the floor to Tomaz. Thanks so much.
Thank you, Marcello. Thank you. It's a pleasure. Thank you for the invitation to give the seminar in this series. So as the title promises, I'll try to discuss some recent results on spectral fluctuations in quantum lattice systems. Let me just start with a sort of motivation slide. Oops. Okay, so basically the idea is, also these slides give a kind of an overview of a couple of related results which became, which we kind of came to in our group. But I will mainly focus, since I wanted to basically narrow my talk, even though the talk should be, at least I try to give a decent introduction and motivation into what and why are we doing this. But still, I try to, give some idea of the proof, since this is mathematical physics seminar. So I skip the 2 and the 3. So I just give a focus on the first bullet here. But just for those who maybe have some broader interest, I just want to point out that this kind of gives kind of broader range of results that I'm going to, that one can discuss using the same tools. So basically, the idea is the following. You have the question is, how can you, characterize dynamics in interacting spin chains, let's say flow-case spin chains in my case. I will discuss periodically driven, but there is periodically time dependent, but discrete in time systems. So there will be, instead of Hamiltonian, there will be a discrete time evolution operator. So, but the point is, how to get some results, like you have results in classical dynamical systems like Kate maps, Baker maps, and so on. These simple explicit textbook results on correlation functions, mixing, ergodicity, and so on. And I was really missing, for many years since I came kind of to, let's say, many body physics, I really missed sort of explicit results on dynamics or on complexity, if you want, in interacting many body systems. So I'd like to view of this kind of simple set of results as kind of the first sort of smoking gun of tools which can address this kind of question. So that this would be like, in caricature, if you want, Baker and Cat maps of many body physics. So and these are the two heroes which are kind of co-responsible for these results. Bruno Bertini, who was a postdoc in our group for 3 years until last year, and Pavel Kos, who has just finished his PhD on the topic of my talk as well. Okay, so as I say, I will basically focus on spectral fluctuations, and I go back to sort of the conjecture which people have discussed extensively in quantum chaos of single particle problems, the so-called quantum chaos conjecture, or sometimes it's also referred to as a Bochigas or Bochigas-Giannoni-Schmidt conjecture. And the conjecture is stating that spectral fluctuations of systems which have some degree of chaos are universal and are characterized by random matrix theory. So the question is, what does it mean that they have some degree of chaos? In this classical kind of conjecture, people refer to systems which are chaotic in the classical limit. So there is a small parameter which you can call h bar or Planck constant, and this parameter you can let to 0, and then the corresponding classical limit should have properties of classical chaos. Then the conjecture states that these spectral fluctuations of such systems should be described by random matrix theory. And then there is a complementary conjecture, the so-called Veritable Conjecture, which states that if systems are integrable, then the spectral fluctuation should be characterized by Poisson ensemble, that is, by uncorrelated events on the energy line or the quasi-energy line. Now, these are the two kind of, the simplest examples, like billiards, for example. You have integrable billiards or chaotic stadion billiards, and level spectral fluctuations are traditionally characterized by level spacings. So level spacing would be Poisson or Wigner-Dyson, which is the kind of or random matrix. And of course, this has been well known, and this is old results. And I will just give you a little bit of light on how people kind of not proved, but understood these results. And then I will go to many-body physics. But before that, let me just introduce the main concept, the main tool that I'm going to use to discuss these spectral fluctuations. And that is also sort of the minimal correlation measure. So for example, if you look at numerical literature or empirical literature, let's say, in this quantum chaos, you find mainly people discussing level spacings because these are the easiest to address from numerical data. But you know, from a theoretical analysis point of view, it's much better to consider a pure point measure, like a simplest two-point function. And the simplest two-point function of levels is the two-point correlation function, or its Fourier transform, the so-called spectral form factor. So for example, this is one slight introduction into spectral form factor, and I'm going to discuss solely discrete time dynamics. So I will discuss unitary, discrete unitary evolution, so which will be which will be generated by a unitary operator U, which you can think of a Floquet operator over one period of the drive. And instead of looking at the spectrum of the Hamiltonian, because the Hamiltonian is time dependent, so one has to look at the spectrum of the evolution operator. That spectrum is spectrum of quasi-energies. I will denote them as phi sub n. So you can start from that. For example, you consider those quasi-energies now as a gas on a circle, because quasi-energies are periodic mod 2 pi. So you start with, let's say, with a one point function, which is the density, and then you define a 2-point function with the distance coordinate theta, and you average over the center of mass coordinate phi, and you subtract the connected part. So you basically it's a connected correlation function, 2-point correlation function. And then you take a Fourier transform of that, and you get what people call spectral form factor. So this is just a Fourier transform of the spectral 2-point function. And what is really nice about this object is that this object can be written in terms of the trace of the propagator. So it doesn't depend on a state; it only depends on the dynamics, on the dynamical operator, on the Floquet operator. Okay. So I mean, this is a two-line calculation. It's completely explicit. I mean, some people also like to discuss this form of this object. That is just a double sum of the quasi-energies, right? This is a double sum over the exponentials of the difference of quasi-energies multiplied by time. This is kind of instructive to understand that after a long time, this becomes kind of a quasi pseudo-random numbers, right? So for let's say after time, which is equal to the inverse mean level spacing, these numbers become all much larger than 2 pi, meaning that this could be understood as kind of quasi-random numbers. So this would be like of the order of the number of levels, right? This is n squared terms in the sum, so it should be order of n. So this gives us what you expect for, let's say, Poisson uncorrelated levels. But for dynamical systems, what you actually have is an exact relation between this object spectral form factor and the trace of the propagator to power t modulus squared. And then you can, if you want, subtract the delta function at t equal to 0. Namely, okay, this is nice, but the problem is that, of course, this formula, as it is written, almost never makes sense because the spectral form factor is not self-averaging. So one has to understand this in a sort of averaged sense. I mean, namely, one has to introduce some parameters in your model and then average over parameters or ensemble of models. Like in random matrix theory, this is very easy because the model itself is defined as a statistical ensemble. But in dynamical systems, one has to still average over some parameter of the model, or maybe it's sometimes or often it is enough just to do moving time averages, for example. Now I'll just give you one slide of results from random matrix theory on spectral form factor. So that is kind of the comparable. I mean, with this, we will compare then our later analytical results. So for random matrices without time reversal symmetry, one should apply the so-called unitary ensemble or circular unitary ensemble, for which spectral form factor simply is proportional to time for times less than the dimension of the Hilbert space or inverse mean level spacing. For systems with time reversal symmetry, one has twice the rate at the beginning, and then it has a smooth crossover to a saturation. Of course, also here one has a saturation for times larger than Hilbert space dimension. And then for Poisson ensemble, one has the flat spectral form factor, which is independent of time, roughly. So, I mean, we have these characteristic indicators, spectral form factor indicators for different ensembles, random matrix, and Poisson. And you see that this is a kind of a very sensitive measure. I mean, for short times, this is extremely sensitive to let's say, I mean, spectral correlations. I mean, spectrum becomes rigid for systems which are chaotic. That's the expectation, or random matrices. So this is characterized by this spectral rigidity, which is small value of spectral form factor compared to Poisson. Very small. I mean, for many body systems, this could be like exponentially small with respect to Poisson value. Now, of course, for typical models, one has to, I mean, this is for random matrices, but for physical models, one has to discuss timescales. And I already mentioned some timescale, which is the inverse mid-level spacing, which is the Heisenberg time. After that timescale, everything becomes kind of pseudo-random, and things saturate to a value which is given by the Hilbert space dimension. But then there is another timescale which people expect in this game, which is the so-called tau-less time. Namely, for times which are short, let's say shorter than the tau-less time, one should see model dependence. One should see dynamics, which is model specific and cannot be universal. So one expects that random matrix sets in only after times which is larger than this tau-less or transport time. So, I will just try to immediately announce that the results which I'm going to get for these particular models, class of models, this quantum many-body cat maps, if you want, for these models, these results have no tau-less time. Basically, they are universal from times 0 or 1 onward. So they can be understood as a kind of critical chaotic systems. So that's why they're kind of amenable to this analytical discussion, I guess. Anyway, so now let me just spend another slide to tell you what people kind of understood for semiclassical problems, for single particle chaotic systems with well-defined semiclassical limit. I mean, this was kind of the main probably driving question which was motivating the whole field of single particle quantum chaos in the 1980s and 1990s and 2000s, essentially. And then people were able somehow to intuitively derive random matrix spectral form factor from periodic orbit theory from semiclassical mechanics. And it all started with the idea of Michael Berry from '85, who first proposed that spectral form factor should be written in terms of, again, double sum over periodic orbits, because the trace of the propagator can be written as a sum over periodic orbits using the Gutzwiller formula, or if you want, just stationary phase approximation to Feynman path integral, which then expands the trace of the propagator of time t as over sums over stationary points, and these stationary points correspond to closed trajectories in phase space. These are periodic trajectories. So then you have this double sum over periodic trajectories because you have trace of u to the t square. And then the question is which term survives from this double sum. And then, of course, the intuitive idea, which was given by Michael Berry, was that one should consider essentially in the first order, in the leading order, only the diagonal terms, which is when the two orbits are paired, which means that they have the same action. And then one immediately gets sort of the leading term of the spectral form factor, which is either t or 2t on these units, which I denote here as tau or 2 tau, depending on whether you have time reversal or not time reversal symmetry in your problem. Namely, when you have time reversal, then you have to pair orbit with itself, but also with its time reversed partner. So you have this 2 tau. Then people have tried hard to improve this kind of idea, to include higher order corrections to spectral form factor, that is to derive not only the leading term, but also the higher order terms. And that was kind of finally recognized by Sieber and Richter. Then one has to include this kind of periodic orbits with more complicated topology, these orbits which have the so-called self-encounters in configuration space. And this kind of people were able to understand that these orbits provide additional interference mechanisms which allow to disclose other terms in the periodic orbit expansion of the spectral form factor. This program has been finally finished by a PhD thesis of Sebastian Müller, who was a student in the group of Fritz Hake. I mean, there was this breakthrough paper in 2004 from Hake group, which finally kind of recognized the full random matrix expansion of spectral form factor in terms of sums over periodic orbits with more and more complicated topology of these self-encounterings. Okay, this was nice, but I want to stress at this point, because my talk is not about this. My talk is about, doing this program for many body systems, for quantum lattice systems. But of course, I will try to convince you that the techniques there are completely different. There is no semi-classical limit and so on. But I want to stress at this point that there is here still work from mathematical physics, namely this result, which is definitely which was definitely groundbreaking, is not a rigorous theorem. Basically, it's just a heuristic statement, if you want. So basically, even for semi-classical systems, there are very few problems where one can rigorously prove that you have spectral fluctuations given by random matrices. One of them being, I think, class of quantum graphs. Okay, so, but yeah, my problem will be about systems with h bar around 1. So spin 1/2 lattice systems or fermionic lattice systems. So imagine you have, let's say, spin chains of spin 1/2. And there also people have looked at spectral fluctuations for many years, for example, at least to my knowledge, since beginning of 90s. Looking at spectral statistics and comparing to random matrix theory has been one of the, let's say, definitions of what people refer to as quantum chaos in this field. So if you look at condensed matter literature from 1993 onwards, I mean, people discuss quantum chaos, they talk about chaotic systems, but what they really mean is that that spectral fluctuations are given by random matrix theory. So one typical example of a Hamiltonian, which displays this kind of transition. I mean, again, one then typically studies Hamiltonians, which are perturbations of integrable systems like this one, which is like a spinless fermion hopping model with nearest neighbor and next to nearest neighbor hopping, and nearest neighbor and next to nearest neighbor interaction. And then when you introduce next to nearest neighbor terms, J prime, B prime, the model goes from Poisson, from integrable, because then it's integrable, it's just equivalent to Heisenberg XX Hamiltonian. Then it goes to non-integrable and then develops random matrix spectral fluctuations like these are Lemma spacings, for example. Okay, and I mean, this is just a picture from a review paper from more than a decade ago. But this is what, there is a vast kind of numerical evidence in the literature that, this is what happens, right? Now, imagine there is no h bar here. There is no small parameter you can tune. So there is one parameter, though, which is the system size. So as soon as you are non-integrable, when you go to thermodynamic limit, you expect that this spectral fluctuation should go to random matrix. But still, I think it's kind of bizarre. Now you have this Hamiltonian, which is a hugely sparse matrix, right, for a system of L sides. This is 2 to 2 the L by 2 to the L Hamiltonian. If you want, okay, if it's translation invariant, you have to you have to reduce it to a sector of constant momentum. But still, it's a huge Hamiltonian matrix, and it is highly sparse. It has only of the order of log of the Hilbert space dimension, non-zero elements in each row or each column. And the number of different matrix elements is maybe just a few, like here it's just 4 numbers. So how come that this matrix has a spectrum which is indistinguishable from random matrix? At least some spectral measures are indistinguishable from random matrix. So that's kind of the question which at least, I mean, I found very disturbing, but also very exciting for many, many years. And I'm really excited that we recently were able kind of to come up with sort of the first mechanisms to answer this type of question. Okay, now this is like how spectral form factor looks like for sorry. It's like spectral form factor for a spin chain, for Floquet spin chain, actually for kick-teasing spin chain, which is one of the systems that I'm going to discuss in the rest of my talk. And this is just to show that spectral form factor indeed, this is for a clean kick-teasing spin chain, which means that there is no disorder, which means that you have translation invariance. So you can use translation invariance to reduce the measure of the space a little bit. But even, that is also, you have an extra parameter to average over, namely the momentum parameter, the overall momentum. So there are different symbols here. These are different quasi-momentum sectors. But then you average over those momenta and you get the curve, which is this, well, first of all, you have this data, which is this sand over there, everywhere, which doesn't make sense, right? And this is basically what you get from numerical simulations. Then what we did here was we averaged over we did moving averaging over time. let's say over windows of, this was like 18 spins. So the Hilbert space dimension was couple 10,000. So then we average over moving, windows of time of the order of 100 kicks. So then what we get is curves, symbols like this, and then we average over the quasi-momentum, and we got a curve which is like this black line behind, right? And then we compare this to random matrix theory, which is this red curve. So you see that you get already a decent agreement, even without any disorder averaging. This is for an individual dynamical system, clean dynamical system, just averaging over, averaging over time, and averaging over quasi-momentum. Yeah? And this is what you get. You get really second 2-point function, which is random matrix. Yeah, on all scales, essentially. Yeah. Okay, then you might ask, okay, this is time compared to Heisenberg time, so this is a very short. You hide very short scales here, but still, I will show you later there is very little non-universal effect at short times. Okay, and then this was like 2007, and of course, as I told you, there was a lot of literature, not so much on spectral form factor, but still on showing random matrix fluctuations. But then I would say only very recently the first kind of papers appeared, which kind of dealt with mechanisms of why random matrix theory applies to these problems. There has been actually a precursor paper from our group in PRX 2018. And then there was a couple of papers from John Chocker's group from Oxford and Andrea De Luca, Amos Chan, who were addressing a slightly different problem. They were addressing Floquet quantum circuits, but random circuits, in the sense that the gates, they considered that the system was generated by quantum gates, and the gates was kind of hard random. And the local Hilbert space dimension was not was a large number. So you might say they had a small parameter, which was 1 over Q, and Q was local Hilbert space dimension. It is not exactly semiclassical limit, but still there is a small parameter, and they found, indeed, they made an exact asymptotic analysis with respect to 1 over Q, and they found that the leading order is nicely reproduced as a random matrix. But anyways, my talk finally, this is kind of end of my introduction, but my talk is about spin 1/2 lattice systems, or low Q or low dimensional, low local Hilbert space dimension quantum lattice systems with strictly local interactions. Yeah? Also the paper I mentioned before from our group considered sort of medium range interactions, so power law decaying interactions, which kind of are easier from this perspective. But the kind of the hardest and most difficult to understand case is really of local interactions. So let me now try to address this problem, and let me try to now first start with the model, which was already mentioned. This Kick-Ising model, which is maybe one of the minimal models in this game. So it has a very simple interaction. It's a model of, again, a 1D, quantum spins, spin 1/2. It's a classical Ising model with a classical magnetic field. So, and then you perturb it with a kicked magnetic field, which is transverse. So, this makes the model quantum, makes it non-diagonal. And of course, this term does not commute with this term. So if you switch these terms back and forth in periodic fashion, meaning that you kick this Hamiltonian with this, let's say, Dirac delta kicks, or in two-step protocol, doesn't matter. It all has the same Floquet propagator, but means that you have a Floquet propagator which is composed of 2 steps, the Ising part and the kick part. Yeah? And the Ising part has just, the kick part has just 1 parameter. This is translation invariant. And the Ising part you assume has, again, just 1 parameter for the interaction, which you call J. So these are one of the important parameters in this class of models, the interaction J and the transverse field B. And then there is the magnetic field in the longitudinal direction, longitudinal fields, which I will assume to be random, pseudo-random, or just random variables, which could be dependent on the side. So it could be side dependent. I will distribute them according to some distribution. This distribution could be very narrow, but still it's important that these are not constant. Yeah? This allows us to make some analytical progress. As I said, this distribution could be very narrow, but okay. So, and this model, of course, is integrable if either of the fields, transverse field or longitudinal fields, are 0. In the first case, is trivial because it's just classical Ising model in 1D. And in the second case, it is slightly less trivial, but still obvious because it is equivalent to you make a Bogoliubov type transformation to map it to spinless fermions, to the quadratic model, to driven quadratic model of spinless fermions. But for generic values of the fields, like both fields, non-zero, this model has no symmetries, actually. no symmetries at all, and it is expected to be non-integrable. And indeed, what we find is that in particular, at least in particular regions of phase diagram, we can show that it is exactly the spectral fluctuations are exactly given by random matrix theory. So I mean, the main thing now, what I will do next now, I will show you how we basically formulate the calculation of spectral form factor for this model, and how do we do disorder averaging. I mean, the main thing is kind of to efficiently treat disorder average quantities with respect to this type of dynamics. Yeah. But before doing that, let me just give you some numerics. I mean, that's always very useful in this game, just to try some numerics in this model, and this is what we get. So, for example, we take this Floquet operator, which I discussed before, for this time-dependent Hamiltonian. We compute spectral form factor, but we compute it as a disorder, as an ensemble averaged spectral form factor with respect to IID magnetic field, longitudinal magnetic fields, which are distributed with a Gaussian kernel, a Gaussian distribution with a mean h bar and the variance sigma. Namely, if you compute that, and this is just a Monte Carlo simulation, so that just make a finite disorder sample, and you compute this average of the spectral form factor. But if you do that for particular values of the spin coupling and the transverse field, which is pi/4, which is kind of maximal, maximal interaction, if you want, is neither strong nor weak, because strong interaction again is kind of, like weak interaction because you have this mod 2pi, right? So this is, everything is kind of cyclic here, right? So this pi/4 is kind of maximum, let's say, maximum coupling if you want. But this not only that, this has additional nice algebraic properties, namely this corresponds to what we will refer to later as self-dual Kick-Teasing model. And in that case, actually what happens is that the spectral form factor, this is for 15 spins, and this is only for time window of 1000 time steps. It shows a perfectly linear ramp with a slope 2. For very short times, you have some fluctuations, but these fluctuations are, sorry for some mess, what happened, okay. For short times, there is some fluctuations, but these fluctuations are related to insufficient disorder averaging and finite size effects. So if you take larger system, fluctuations go down. If you take stronger variance of disorder, fluctuations go down. But in either of the limits, they go to 0 for the non-vanishing disorder. So actually, this is actually a result of our analytical analytical result. So I'm just, numerics cannot see that, but you see that you can prove theorems, and then you see that these things have to go down. Okay, so now before just giving you the more general statement and the idea of the proof, let me just give you the simplest statement which we can prove for this Kick-Teasing model, namely what we can prove that for odd times, and that's actually funny because the system corresponds to different universality classes for odd and even times, and slightly different. They have the same spectral form factor though, they're still in the asymptotic limits, but still they are different universality classes strictly. And for odd times, we can prove the results, saying that spectral form factor in thermodynamic limit is equal to 2t for times larger than 7. And 2t is exactly the linear ramp of random matrix theory. And for even times, as I said, we have a slightly different universality class, and we cannot really prove anything yet, but we have a conjecture that asymptotically spectral form factor goes like 2t plus 1. Of course, this plus 1 becomes irrelevant as in the asymptotic limit, but still it's curious. We can actually understand why this one happens, but still we cannot understand that there is no other term which would add to this one. Okay. So so let me just slightly recap this result. So what we have shown is that results, this theorem applies for any value of the disorder averaging strength. So it's independent of the variance sigma. So the model is disordered. The model is ergodic for any strength of disorder, which means it has no Floquet MDL if you want. And we can take in particular the limit of a clean system at the end of calculation. So if you want, you can take the limit of a clean system, but it has to be the last limit of your calculation. And moreover, result is independent of the average of disorder strength, the average value of the longitudinal field. So we can actually even expand around the integrable point, which is setting h bar to 0. Okay, now just one slide of kind of key idea how one approaches the proof of this statement. And the idea is just to rewrite the trace of the propagator, I mean the propagator, which is the Floquet operator to power t, as a partition function of a 2D statistical model, which is in this case just a 2D Ising model with inhomogeneous magnetic field. I mean, this is exact statement. I mean, this is exactly the 2D statistical model. This is exactly the 2D Ising model with magnetic field, but the weights are not real, not positive, but they are in principle complex. But algebraically, it's just a 2D statistic, it's just a 2D Ising model with inhomogeneous fields. And these fields are homogeneous in time, but inhomogeneous. So this is a 1 + 1 dimension. One dimension is time. In this case, the spatial dimension is vertical, and time dimension is horizontal. So the field is constant in horizontal direction, but is disordered in vertical direction. And what you can do now.
Can I just ask a question here? So the time is discrete in your case?
The time is discrete, yes, it's Floquet system, so time is discrete.
But it does not need to be.
Well, that's actually important in the tricks that we are doing, because you could, of course, think of trotterizing any evolution in discrete time, but this will not have this neat property of being self-dual with respect to exchanging space and time.
Right.
I'm coming to that. I have not yet mentioned what I really need for my ideas to work, but it's actually important to be able to switch space and time. And this you can only do with a finite time step and some additional features. So you cannot do the continuum time limit, so you cannot approach Hamiltonians. And that's a very important point. And I mean, we can discuss at the end, because it's kind of interesting question what one can do in the Hamiltonian systems. Okay, in any case, so now, yeah, what one needs now is just to be able to rewrite this. Now, you see, this trace of u to the t is like a partition function of Ising type to the model with non-positive weights. You can now write it as a trace of the product of a power of a unitary matrix, or you can write it as a trace of a power or a product of other matrices which have exactly the same algebraic structure. I call them u tilde of Ising, but with different parameters. Because this model, it's a 2D Ising model. You can just think of one direction as, contracting direction, which can be either space and time. So in the usual case, the contracting direction is time. So then the propagator is just the quantum dynamics, but the contracting direction can be space. And then the propagator is something which I would call space dynamics. And this space dynamics can be unitary or not, but it so happens in these models that it is unitary when these parameters, the coupling parameters, have value pi/4. So that's the dual point, self-dual point. It's actually 4 points plus minus pi/4 for both. So in that point, this dual propagator, the space propagator, is unitary as well. And that's very nice. And I will show you later why it's nice, because I can't do everything in this talk, but I could focus on the Ising model, but I would rather do it in more general setting in a minute or so. But that's really nice, because it allows us then to treat multi-replica systems, right? I mean, now this is just a trace of u to the t, but what we need now to do to address spectral form factor is to consider two replicas, trace of u to the t times trace of u to the t conjugate, and then they do the disorder average. But when we do this space-time flip, then we can do the disorder average locally, mainly within each step of the space dynamics, if you want. Okay, let me try to be really explicit in the next kind of example. But from this, the take-home message from this slide is that you need a dynamics which can be flipped so that you exchange space and time and still being unitary. So it's a kind of strange thing. It's not like, relativistic invariance. It's much more rigid and it's discrete. I mean, it's only possible to define it on discrete lattices. But you need to be able to flip space and time and keep unitarity. You may think this is crazy and this never happens, but no, I mean, it happens in this model. And actually it happens in a large class of models, in a, let's say, not so small class of models. And these models we termed as dual unitary circuits. So, and that the Ising model I discussed earlier is just a special type of a dual unitary circuit. So that's discussed in this PRL of our group, from 2019. And the idea is the following. Just imagine you have now circuits generated by 2-qubit gates or 2q-d gates. I denote by d local Hilbert space dimension. And imagine now, I should apologize because from now on, I will consider time going vertically as usual in this field of tensor networks. Time usually goes vertical. So now imagine you have this 2-on-2 gate, which means you map states I times j to states k times L. So that's a unitary which maps pair of states to pair of states, or a joint state of ij to joint state of kl. That's a unitary over the square dimensions. But now, of course, you can flip space and time, and you can consider this as a unitary which maps ik to jl, and you define it in this way. So you define some sort of a tilde transposition, which is basically related to partial transpose, if you want, times a swap. But then in any case, I prefer to define it like this, because this is now really a flip, which now defines this gate to go not bottom up, but left right. Yeah. And now you ask that this gate to be unitary, not only when it's considered bottom up, but also when it's considered left right. And these gates, which have this property, we denote as dual unitary gates. So these gates actually are related to concepts to some concepts in quantum information theory, like unitary channels. And the classification of these dual unitaries is hard. It's not known. But I will tell you later that we can classify these dual unitary gates for qubits, for example, at least. Now, let's build circuits out of these dual unitaries. So now, again, we make brickwork circuits. You take a layer of qubits, like a tensor product of, that is now a spin chain of size 2L. And now we take a layer of L tensor products of a fundamental gate, and then we have a shift and another tensor product, and again a shift, and so on and so forth. So this would be like 2 time steps of a Floquet protocol generated by this dual unitary gate. But you see, again, this you can view this kind of space-time fabric. You can now view again as a transfer matrix. You just take a trace with respect to space and time, and this is like a partition function of a 2D statistical model, which you can evaluate in terms of transfer matrix in either space or time. So now, if you contract it with respect to the usual dynamics, then it's like trace of u to the t. But then you can define the u tilde, which would be the horizontal propagator, which would be, again, having the same structure, like this tensor product shift, tensor product, the inverse shift. So again, a brickwork structure. And now you can define, you can evaluate this trace of u to the t in 2 ways, either forwardly in time or forwardly in space. And you see what, again, this dual unitarity buys us is that this guy is unitary. So both transfer matrices are unitary. And this is important, and that's actually very useful, as you will see. And this is generalizing this feature of Kick-teasing dynamics from before. Now, just as an intermezzo, let me now show you how to classify all these dual unitary circuits, or dual unitary gates for qubits. In general, this is a hard problem, and solution is not known. But for qubits, this can be done very explicitly. The starting point is a general parameterization of U4 or SU4 gates, 2-qubit gates, which can be written in terms of the Heisenberg gate times a tensor product of 2 SU2s on the left and 2 SU2s on the right in the phase. And this Heisenberg gate, if it's restricted to a gate which has 2 coupling constants, Jx and Jy equal to pi over 4, and the third one, let's say Jz equal to J arbitrary, then this becomes dual unitary. So you see that dual unitaries in this parameterization are just submanifold of SU4 or U4 of codimension 2. Just have to fix 2 parameters. So it's not such a strong restriction. And after that, if you restrict to that set of gates, you'll get unitarity both in space and time. And examples, of course, are from very trivial like swaps to something integrable like trotterized XXZ chain, which is related to R matrix of 6-vertex model, which can be made unitary in both directions at particular values of coupling constants, or self-dual Kick-teasing model, as I discussed earlier, can also be written explicitly in terms of dual unitary 2-on-2 gate. Okay, if there is any question, please ask. I understand it's a lot of concepts I am trying to introduce, and I will somehow use. So if there is anything, please.
So, Tomaz, did you say that this is the unnecessary and sufficient condition for the self-dual unitary for qubits?
Yes, indeed.
Correct. Okay, so correct. This is the shape.
For the qubits, that's all there is. Yes. And for Q dits, we have some maybe conjecture, I mean, that for almost complete parameterization, but I think it's a hard problem. I mean, one can try to, I mean, yeah, maybe I could discuss this at the end of my talk, but yeah. For Q bits, this is the statement, which is, I think, precise. Okay, good. So now let me go now to spectral form factor of these dual unitary circuits. Now let me just now to slightly generalize the problem of computing spectral form factor for this type of models, going from Kick-teasing now to arbitrary dual unitary circuits. So actually, I will not do it for completely arbitrary circuits. I will do it for slightly restricted circuits, which means I will take fixed dual. Oops, this is sorry. I will take this kind of propagator, which is now one time step layer of the circuit, right? This is a Floki operator, which is composed of two qubit gates, two dual unitary qubit gates, which are this light and I mean two green boxes, two red boxes, which one is dark when one is darker than the other, which means these two guys can be different. This would be this U and W, the two gates. And then they could be decorated by these circles. So these circles are the single qubit gates. So these single qubit gates are gates which carry disorder, if you want. I mean, they can be different at different sites, and they will be in general different at different sites. And the only restriction which I have in this model now is that this disorder is IID. So that is, these disorder gates are uncorrelated, are different at different sites. But they are single site. They are not interactions. So interactions are homogeneous in space. I mean, yeah, in space and time, if you want. I mean, they have periods too, but otherwise they're homogeneous. Then they are decorated by single site disorder, which is only random in space, but not in time. And then you can, and then the goal of this game is to compute this spectral form factor, which is now the expectation value with respect to this distribution of single qubit disorder unitaries, trace of u to the t modulus squared. And this I can immediately write in a different way, because these gates are dual unitary. So now I'll immediately rephrase this in terms of the space propagator, which is again unitary, right? And this allows me to, if I rewrite this in terms of, first of all, I write this in terms of two replicas, right? It's a tensor product over two replicas, trace of the tensor product to power t, and then I do the space-time flip, and I rewrite this as a partition function contracted with respect to space transfer matrix. But now the space transfer matrix has disorder. I mean, now the fields, I mean, these random unitaries, the local random unitaries are IID. So I can, they are independent, uncorrelated. So I can do the averaging independently, which means I can put averaging inside and do it before I do the power. So basically I can rewrite it, everything in terms of the trace of something which I call now a spectral form factor transfer matrix, WT to power L. Okay, let me just give you the.
Excuse me, what is capital T?
Capital T is, sorry, it's just a transposition. Yeah.
Oh, okay, okay.
I got confused with that. Yeah, it's just a transpose. That transpose actually is actually not even, well, yeah, here it's probably rather relevant, but yeah, in any case, yeah.
So transpose, not the Hermitian conjugation.
Not the Hermitian conjugate, no. The dagger will be Hermitian conjugate and T will be just a transpose. Yeah, sorry for not explaining this. Maybe not so orthodox notation, but yeah. Okay. So now let me just give you this in terms of diagrams. So because this tensor, I mean, everything can be just phrased in terms of this diagrammatics of tensor networks. So this form factor now, which is the expectation value over product of two traces, is like expectation value over product of two replicas of this partition functions. And now so now what happens is that this disorder, of course, is different from point to point in space, but it's all the same. I mean, it's the same in every other layer in time. I mean, this time has two half time steps. So this ball is the same as this ball is the same as this ball. and this ball is the same as this ball, and so on. It's the same as that ball behind which is this ball, and so on. It's periodic boundaries in space and time. So you take these periodic contractions. This means these are indicated by these dashed lines behind, and that's what it is. Yeah. So, so now, but you see, I mean, since these guys are IID, now I can do the following trick. I can just split this into pieces, which is now, I mean, just diagrammatics of that formula at the end, right? Now, and this is the way I define this SFF transfer matrix, right? And now this is, I mean, this is now will be the key object, which I will analyze later. So, I mean, the idea now is basically just to make sort of precise spectral characterization of this transfer matrix. This transfer matrix, now we can go to thermodynamic limit because now space becomes time and time becomes space. So now for finite time, this has a finite size. It's a finite lattice of size t. But then we have to go to thermodynamic limit. So if you want to address the problem of computing spectral form factor for any finite time in thermodynamic limit, you have to make precise spectral characterization of this transfer matrix. So to understand its leading eigenvalue and the gap. So this is what we're going to do next. Yeah. Okay. So now that's sort of the curriculum. I mean, the picture of how these things are defined and one needs to compute. Okay. So now this will be kind of the last part of my talk. I think I'll be probably just needing maybe 10 more minutes. So if there is any question, maybe about definitions, maybe I can clarify this before, because then I'll just go into the statement of the theorem and the idea of the proof. Okay, so now the idea is, how to compute that. And basically, as I already showed you before, I mean, we phrase the computation of spectral form factor as the trace of some transfer matrix to power L. And, this is a hard problem for arbitrary L, so we go to thermodynamic limit. So one has to make sure that one appreciates that. I mean, this is a sacrifice. We go to thermodynamic limit, which means we can only address short times. We can only address times which are much smaller than the Heisenberg time, because we take thermodynamic limit first, as usual in statistical mechanics. But still, I mean, here is a kind of, something that maybe you don't want to do. Maybe you want to also understand time scales of the order of Heisenberg time, but for that you would need different methods. So this method allows us to compute things for finite, arbitrarily long time, but in thermodynamic limit. So, okay, so now, but again, to be able to make precise statement about behavior of spectral form factor, then what you have to do is to count how many eigenvalues one of this transfer matrix you have, because each eigenvalue one gives you a contribution of one to spectral form factor in thermodynamic limit. And next, you want to show that there is a gap between eigenvalue one and the rest of the spectrum. As soon as you show that there is a positive gap, you show that in thermodynamic limit, this is irrelevant. So the spectral form factor is just counting function of eigenvalue one. Okay, so now let me just phrase this as a kind of theorem, which we have proven in this recent paper. So the theorem is slightly more general. We prove it for arbitrary Hilbert space, local Hilbert space dimension, but I'm only spelling it out for qubits for simplicity. So the idea is the following. Let's take a distribution of IID local 1 qubit gates, which are denoted as U sub x and V sub W sub x, where x is the position, which is running. Again, I may want to remind you how I enumerate sites. So sites are enumerated by half integers. So since there is this staggering structure in the problem, these are left wires are integers, right wires are half integers. So it goes from 0, 1/2 to, let's say, L minus 1/2. So it's 2L sites indicated by half integers from 0 to L, or L minus 1/2. And right, so now this, so the statement is the following. So for arbitrary distribution of local gates, arbitrary, let's say, smooth and non-singular distributions, which can be precisely defined, which are distributions over, let's say, SU2 with smooth BDFs over SU2. And for any dual unitary 2-qubit gates, U and W, sorry, I mean, I should probably take also arbitrary U and W. I mean, just other than the swap. So this U and W should be different than the swap. We have that the spectral form factor can be understood as the dimension of the commutant of a simple set of operators, which are given as local magnetizations and spin interactions with support 2. So these are on a ring, on a periodic ring. These are translation invariant and are given on are defined on periodic ring of 2T sides. So this ring again is labeled, the sides of the on the temporal ring are again labeled by half integer. So tau goes from 0 to T minus 1, and it's periodic with respect to shifts by two sides by complete period. There is two lattice sides. So tau goes over integers, but then it's either shifted by 1/2 or 0. So these are local magnetizations, and these are local spin interactions. So if you consider a set of operators composed of local magnetizations, components of magnetization, A goes X, Y, Z, or local spin interactions, if you consider the set of operators and you ask what is the commutant of this set, what is the set of operators which simultaneously commute with all those guys, then the statement tells you that, statement of the theorem tells you that the set of this, the commutant has exactly T elements, and these T elements are the cyclic shifts by integer, by even number of sides on a spin ring of size 2T. So they are basically just shifts by integer on this half integer lattice. All possible shifts by integer, right? These are given to the operators which simultaneously commute with this set. Okay, and right, clearly, I mean, a subset of the commutant is already, it's obvious that it's spanned by T integer side translation operators. I mean, the crux of the proof is to show that there are no other elements in the commutant. There is no other operators which simultaneously commute with all these guys. Okay, so yeah, for the end of my talk, I'll just give you kind of a two-slide introduction into the proof of this statement, because it's not very, I would say it's not very deep, it's completely elementary. So I guess at least the main idea could be followed. And it has a couple of elements which maybe are worth stressing. So first one has to reduce first of all, one has to reduce this problem to let's say simpler algebraic, or at least simpler looking algebraic problem. So for example, one can relate the problem of for any eigenvalue which is on a unit circle. So again, I have this decomposition. Okay, sorry. So the first thing is to write this double transfer matrix as a composition of a unitary on a two replica space times some averaging operator times another unitary times another averaging operator. And this averaging operator again is a product of even side and even sublattice and odd sublattice averaging operators. And these averaging operators can be written as, you know, in using this PDF or SU2. This theta labels the, let's say, the angles on the SU2, the directions, I mean, if you want, in a ball, which defines SU2 in this case. And this is just, again, these are just components of magnetization on the even and odd sublattice. So this, one of these indices, iota, denotes which sublattice, and the other denotes in which half time step. So these are two half time step, half space steps, if you want, in this case. Okay, it's a bit, sorry, it's still a bit kind of tricky technicality, but you know, the main point is to appreciate that one can factorize this transfer matrix into something unitary and something which is a non-expansive map. So it's immediately obvious that this thing should have spectrum which is inside unit disk. If this W tilde, if these dual unitaries, I mean, remember these guys are the space propagators, they are propagators in the space direction. So if the original gate was not dual unitary, these guys would not be unitary. So I could not make this statement that this dual transfer matrix is a contraction, that it's non-expansive map. So that's sort of the first kind of thing that this dual unitarity buys me. Yeah. And the second thing is like a simple lemma, which we call lemma 1 in our paper, which isolates unimodular eigenvalues from the rest of the spectrum. It allows us to characterize them very precisely. That is, for any dual unitary circuit, which is this form, this SFF transfer matrix fulfill the following properties. First, which I already explained, is that the spectrum is within unit disk. And second, for each unimodular eigenvalue, which then corresponds to eigen operator A. I mean, I can understand this A as this vector A as an eigen operator, as you will see later, but in this case, it's just an eigenstate. This guy should be simultaneously an eigenstate of the unitary part and of these pieces of the generators of this contraction, which are kind of commutators with the, this already smells of commutators, right? Now, and Right, and then the third point, maybe I can skip because it's technical and not relevant. But you see, I mean, the next step, what one needs to do is now just to do the unvectorization. This is like a vectorized map. So now I just do the unvectorization and just understand this eigenvector as an operator, as an eigenoperator. And now this becomes then just the first equation becomes just this one, right? It will be just an eigenvalue equation or eigenoperator equation, or the fact that this A should phi commute with the product of these unitaries. And then these other equations for each eigenvalue modulus 1 should correspond to the fact that this A should simultaneously commute with all components of mathematization and mathematization interactions. Well, no, in this case, it's just mathematizations. Yeah. Okay. Right. So now, but then in the next step, we'll use explicit parameterization of these dual unitary gates, which I was discussed in one of the earlier slides. So in here I use slightly different parameterization, but it's the same as before. This is the Heisenberg gate with Jx, Jy equal to pi over 4. It can be written as a swap times an Ising gate. It's a swap times an Ising gate for both guys. And then there is this U1, U2, U3, U4, and W1, 2, 3, 4, which are just the local, I mean, which are just the single qubit SU2s, which you can use to decorate those interactions. And for those particular parameterizations, then the above condition can be polished to what we call lemma 2, which says that for J, J prime, both different from 0 mod pi, this condition above can only be met, cannot be met unless phi equal to 0, which means that we can only have eigenvalue 1 on a unit circle. Only unimodal eigenvalue is eigenvalue 1. And for that, these conditions are then equivalent to the statement that A should commute simultaneously with components of mathematization and with two-side interactions, nearest neighbor interactions. Right, and now this is already kind of mapping the problem to the problem of characterizing the commutants of this set of variables. Now, the next step is to consider a multiplicative algebra, which is generated by this set, and to show that representations of this algebra over subspaces, which corresponds to momentum subspaces, that is eigenspaces of two-side shift operator, are irreducible and inequivalent, right? I mean, so what we do now is to make a Fourier decomposition. We just look at the eigenvectors in this time space, which corresponds to eigenvalues of translation operator in time, the so-called time momentum or frequency, if you want. And we show that any pair of states in this subspace can be connected by a sequence of elements from this algebra, from this set. And then the rest is just to apply the Schur's lemma to show that this implies that there is no other element, no other operator which would simultaneously commute with this set. But this element should be block diagonal. Okay, yeah, with this, I mean, this is kind of the sort of the proof in the nutshell. So I think I will slowly try to conclude. I just maybe want to mention for the end that there has been a couple of other recent developments using this concept of dual unitary circuits, which were kind of interesting. In particular, in the group of John Chocker, they have looked at, they have tried to characterize many-body localization in terms of the spectrum of the dual SFF transfer matrix. They call this spectral Lyapunov exponents. And the transition to localization can be characterized by transition in these Lyapunov exponents, kind of, yeah. And one can also characterize this recent development on non-equilibrium phase transitions in measurement circuits in terms of dual unitary circuits. This was in the group by Vidika Kemani and Grover. And in the group of Dima Abanin, they looked at this, what they call, again, I mean, it's related to a concept of leading eigenvalue, eigenoperator of this dual transfer matrix. And it, yeah, okay, so never mind. I mean, it's again something related to this dual unitarity. And then in the last paper of our group, we have tried to characterize the perturbative stability of these dual unitary circuits with two perturbations which break dual unitarity. So I think that's kind of also a very interesting and important question, is to understand how special are these results and how structurally stable can they be with respect to generic perturbations. So if you just make your gates a little bit different than exactly dual unitary, how much of this physics can still survive. And of course, this, I mean, maybe one can have some naive intuition that this might be more structurally stable than integrability, for example, but that has to be shown. But in that PRX that I mentioned here, we have shown kind of a subclass of this type. I have no time here to enter into that, but I can maybe discuss more in the discussion. But at least there is a subclass of this type, a subsystem of this type, which is structurally stable. That means, for example, computation of correlation functions, 2-point correlation functions, is stable with respect to perturbed dual unitarity. Okay, with this I would like to conclude. So again, as a bottom line, I presented what I believe are the first exact results on spectral statistics of extended quantum lattice systems when thermodynamic limit is taken first. And that is a kind of a drawback of this analysis, that thermodynamic limit has to be taken first. So this gives me the main challenge for future work, which is try to find some method which would apply also for finite systems, which would give us systematically finite size corrections. And why such method would be so, I mean, of course, one would be able to address timescales closer to Heisenberg time, but moreover, one would also be able to address other statements in, let's say, non-equilibrium dynamics of interacting many-body systems, for example, like eigenstate thermalization hypothesis. Maybe one is tempted to believe that these dual unitary circuits can also serve as kind of toy models of where ETH can be proven. But of course, one first has to understand how one can break this order of limits, because to prove eigenstate thermalization, one has to control time to infinity limit before taking thermodynamic limit. And that seems to be, at the moment, at least to my side, out of reach. So with this, I would like to thank for your attention and take questions, if any.
Thank you very much, Tomaz, for this very nice talk. Is there any question or comment from the audience?
Yes. Yeah, it was very, very interesting. So, but I still don't understand the role played by the randomness. So I understood that you can take random average this way very cleverly, but can't you do without randomness? So what is the role?
Well, I think, yeah, I mean, for computation of spectral form factor, randomness is crucial, because I think the concept itself requires randomness because it's not self-averaging. So we have to introduce.
Okay, so is that a physical reason or a mathematical reason?
That's not very physical, no, because we can address other quantities which don't require averaging, and we can again use the same trick to evaluate things to the very end. For example, in these simple 2-point correlation functions of local observables, if you want dynamical structure factors, you can compute them for dual unitary circuits exactly analytically. So you can compute them using a zero-dimensional quantum channel. So you can replace computation of dynamical correlation function in a 1+1 dimensional quantum lattice system with something which just requires you to evaluate iteration of a 1-qubit quantum channel. So, and again, I mean, this is simply application of this concept of dual unitarity. So that was actually the point of that PRL, which I quoted when I defined dual unitary gates. So that can be done, and for that you don't need any averaging. And then there are other things like operator spreading, which also we referred to in some papers, and there were some other papers I didn't mention. Some other people look into that, and then again you can provide some results without averaging for operator spreading for, let's say, Renyi entropy of operator entanglement entropy. But yeah, but for spectral correlations, I don't see way around this averaging.
Okay, thank you.
So actually, I have a question about what you were saying at the end about doing perturbation theory around those dual points. I mean, is there some evidence of universality of the spectral form factor, or is it reasonable to expect something of this type?
Well, that's, I think, yeah, that's a very interesting question. I think it's not even, I mean, I'm not even yet clear to me how precisely to ask this question, but yeah. Suppose there is some sort of structural stability of these dual unitaries. Of course, this is not just like universality class of spectral fluctuations, because we know that we have much broader class of universality class of spectral fluctuations. I mean, the random matrix theory applies beyond dual unitaries, right? It's just that you have to introduce additional timescales. These dual unitaries are even more universal because you don't have to have any tauless time. They apply it from shortest timescale onwards. But suppose now in this PRX we discuss exactly that. So suppose that there is some universality class of dual unitaries, which means that are, stable under some sort of space-time RG. And this would be like a dual unitary universality class. So which means that this will be something that is structurally stable, that's attracted to the dual unitary circuit under Petrov. I mean, even if you go away from it. But certainly this cannot include Hamiltonian, continuous time Hamiltonian dynamics, as I tried to explain in one of the questions earlier. So certainly not, it cannot include any dynamics in 1 + 1D, of course. I mean, we know that the correlations are very special. So, but at least it could be some universality class, not just some isolated models, which low dimensional manifolds of some models.
Yeah.
But it's to be discussed. I mean, it's to be studied. It's not clear.
Okay, thanks. Other questions or comments?
So perhaps one question, if I can.
Yeah.
Yes, please.
So it would be much easier to study the system with the imaginary. Would it help? Can you get anything?
With imaginary time, you mean?
Yes.
Well, I mean, I don't imagine how you can get, because then you lose unitarity already for the first, I mean, then you don't have unitarity even in time evolution. Maybe you have something else. I don't know. I mean, yeah, this is something.
Well, but I mean, for exact solutions of, I mean, definitely when this is equivalent to an Ising spin system, then you would have access to all the probabilistic tools, including.
Yeah, no, I understand what you want. Yes, of course. I mean, you want to have something which is now basically a stochastic matrix, right, rather than unitary.
Yes.
And then you want, of course, you can, for example, in this PRX, we discussed this kind of idea of dual bistochastic systems. So you can think of systems which are stochastic or bistochastics in both directions, right? When you take a circuit of, let's say, Markov circuits, if you want. I mean, many-body stochastic systems which are implemented as two-side Markov gates, right? But these gates might not be unitary but stochastic, yeah. But now they can be stochastic in both directions, so they can be bistochastic. I mean, dual bistochastic, right? First of all, they have to be bistochastic, meaning that they have to be stochastic and its transpose has to be stochastic, but they also have to be dual bistochastic, meaning that if you free space and time, it will be bistochastic. And that actually has been explored in this PRX, and that's exactly the small corner of these models for which we can show structural stability. So actually what we do is we take a unitary model and we average it over longitudinal fields. If you average over space-time random longitudinal fields, then it becomes classical stochastic model. Then it becomes like a diagonal, like a spin chain becomes like now something which is mapping diagonal operators to diagonal operators, so it can be replaced by a classical stochastic model, which is exactly dual bistochastic if you start with dual unitary spin chain.
Yeah, and then the important thing is that you can transfer the results you get for imaginary time back to real time.
Well, that I'm not sure, because I mean, this is, I mean, yeah, I have not really at the moment I have not really any intuition whether this might work, because I don't know if this could, no. I mean, what you ask is of course different. If you already rotate time to imaginary time in the beginning of this calculation, and then, because for what I said now, I mean, we start with real time and then we do this order averaging, yeah. And this order averaging or noise averaging maps the problem to classical stochastic problem. But if you do something else, if you do just a complex rotation of time, maybe you gain something more. I don't know. It's definitely an interesting question we have not thought about. I mean, I don't know.
Thanks.
Other comments or questions from the audience? So it doesn't seem the case. So thanks a lot again, Tomaz, for the very, very nice talk.
Okay, thank you all.